Oxidation and reduction reactions. Living creatures, like humans, exist between a balance of oxidation and reduction reactions called redox reactions. The process of oxidation is widespread as seen in fires and rust. Redox reactions have a number of similarities to acid-base reactions. Like acid-base reactions, redox reactions are always a matched set. There cannot be an oxidation reaction without a reduction reaction happening simultaneously. Similar to acid-base reactions that involve the transfer of positive charged protons, redox reactions involve the transfer of negative charged electrons. When molecules are ionized, there is a transfer of electrons between the atoms, causing the molecule to split into positive and negative charged ions, which attract each other and connect together by an ionic bond. An example is sodium chloride or table salt, where the bond between the sodium ion and the chlorine ion is an ionic bond. When molecules are oxidized or reduced, electrons are not transferred but rather shifted towards one of the atoms and away from the other, causing the molecule to be polarized. They are bonded together by covalent bonds. An example is hydrogen chloride in hydrochloric acid and water, where chlorine and oxygen oxidizes hydrogen. The word oxidize comes from oxygen, since molecules with oxygen show this property so well because of their high affinity for electrons. Other atoms also have high affinity for electrons and are also capable of oxidizing. An example is hydrogen fluoride, where fluorine oxidizes hydrogen, causing it to be polarized. Oxidation is the loss of electrons or an increase in oxidation number by a molecule, atom, or ion. Reduction is the gain of electrons or a decrease in oxidation number by a molecule, atom, or ion. The oxidation number is an indicator of the degree of oxidation or loss of electrons of an atom in a chemical compound. Conceptually, it is the hypothetical charge that the atoms would have if the atoms would be ions connected by ionic bonds instead of just being polarized connected by covalent bonds. The reductant transfers electrons to the oxidant. Thus, the reductant or reducing agent loses electrons and is oxidized, and the oxidant or oxidizing agent gains electrons and is reduced. Substances that have the ability to oxidize other substances or cause them to lose electrons are said to be oxidative or oxidizing and are known as oxidizing agents, oxidants, or oxidizers. Oxidizing agents shift or remove electrons away from other substances and are thus themselves reduced. Oxidizing agents are called electron acceptors. Substances that have the ability to reduce other substances or cause them to gain electrons are said to be reductive or reducing and are known as reducing agents, reductants, or reducers. Reducing agents have their electrons shifted or transferred toward other substances and are thus themselves oxidized. Reducing agents are called electron donors. Many oxidations involve the addition of oxygen atoms or the removal of hydrogen atoms from and to organic molecules. Functional groups can be arranged in the order of increasing oxidation numbers indicating an increase of oxidation. For example, the oxidation number for alkalines is -4, for alkenes, alcohols, alkyl halides, and amines it is -2. For alkyne, ketones, and aldehydes it is 0. For carbonic acids and amides it is +2, and for carbon dioxide it is +4. Most oxidations are conducted with air or oxygen. Thus, when an alkaline like methane is oxidized to carbon dioxide and water, its oxidation number changes from -4 to +4. The large increase in the oxidation number is clearly shown by the high heat and bright light given off in the combustion. Many important biological processes involve redox reactions. Biological energy is frequently stored and released by means of redox reactions. Photosynthesis involves the reduction of carbon dioxide into sugars and the oxidation of water into molecular oxygen. The reverse reaction, cellular respiration, is the oxidation of glucose to carbon dioxide and the reduction of oxygen to water. Oxidation slowly turns us from sweet babies into sour old people, just like it turns sugars into alcohols in wines, and eventually into acids in vinegars, and finally into carbon dioxide and water. Oxidation, like in a fire, breaks something complex, like a life, into something simpler, like ash and earth. Pure nonmetals tend to be oxidizing agents that oxidize other elements. The best oxidizing agent is oxygen. Reduction, the opposite of oxidation, acts like water poured over a fire. Many pure metals tend to be reducing agents that are oxidized. The best reducing agent is the simple electron. Many enzymatic reactions are oxidation-reduction reactions in which one compound is oxidized and another compound is reduced. The ability of an organism to carry out oxidation-reduction reactions depends on the oxidation-reduction state of the environment or its reduction potential. Redox affects the solubility of nutrients, especially metal ions. Just as the transfer of hydrogen ions between chemical species determines the pH of an aqueous solution, the transfer of electrons between chemical species determines the reduction potential or redox potential of an aqueous solution. The redox potential, Rh2, of a substance is a measurement that determines the amount of available electrons it contains. This tells you its vitality or energy potential. The scale used in the measurement goes from 0 to 42. Values above 28 are considered oxidizing, below 28 reducing. Water, optimal for health, should have an Rh2 value of between 24 and 28, slightly on the reducing side. Fluorinated water supplies have an Rh2 value higher than 27. Mineral water has an Rh2 equal to 30, while tap water has an Rh2 equal to 34. The relationship between Rh and pH is Rh is equal to ORP plus 200 divided by 30 plus 2 times the pH value. ORP is in millivolts and is a measure of the ratio of oxidized to reduced materials in a substance. ORP may vary between plus 800 millivolts, indicating a strong oxidizing environment, and minus 300 millivolts, indicating a strongly reducing environment. ORP decreases with increasing pH at about 59 millivolts per pH unit. High values indicate oxygen-rich environments with many oxidizing compounds such as iron oxides, nitrates, and sulfates. Low values indicate oxygen-deficient environments with reducing compounds such as iron ions and organic matter. Alkaline water has more reducing agents that give it antioxidant properties and measures low ORP. Acidic water has more oxidizing agents and measures higher ORP. The ORP of most tap water in the USA is between 150 to 600 millivolts, and thus is an oxidizing agent. Air, food, and water all have ORP values, which can be measured by an ORP meter. Substances with a positive ORP are robbed of their electrical negative charge and have no antioxidant abilities and cannot assist your body in the fight against free radicals. The more negative ORP they have, the more they can neutralize any excess free radicals that need to be neutralized.